Hello everyone, today we're going to be looking at the defining properties of waves, things that make things like sound waves, light waves, even water waves, things that we're able to measure with those things that all of those things have in common. So we're going to be looking at just kind of the basic characteristics that define how a wave moves and what we can measure about a wave. And then later on, we'll look at some more specific examples of what waves can do. So this is going to be called Properties of Waves. You can add that to the top of your notes. And I've really kind of broken this into 4 different sections, and we're going to look at just the first 3 of those today. So we'll look at the different parts of a wave, what we're talking about when it comes to wave frequency and wave period, and then 2 different types of waves that you should be able to identify. And so kind of moving into this first section is we're going to look at the various parts of a wave. And by the end of this section, you should be able to identify a couple of different important pieces. So I'm talking about the crest, the trough, the amplitude, and the wavelength of a wave. So there's 4 kind of pieces that you should be able to identify if I give you a diagram of a wave. And so let's kind of go ahead and get started with just what is a wave. There we go. So a wave is a means of transferring energy and information from one point to another without there being any transfer of matter in between the 2 points. And waves move through something called a medium. So to kind of put this in context, I want you to think about your cell phone. Your cell phone connects to the internet. It connects to its cellular network through radio waves. That's how we get information on and off of that device. Every time you download a video or an app or you receive a text message, we didn't move something physical onto your cell phone. Your cell phone doesn't get heavier every time that you scroll through TikTok or Instagram. And I think that's a good comparison to make, because for a long time, if a human wanted to send information from one place to another, they had to write it down as a letter, and they sent it to some place. So there was a transfer of mass that happened. And there was, you had to move a physical object from one place to another. Waves enable us to do this without moving a physical object. And so that does allow us to move information without making the end thing heavier. And I think all of us are grateful for the fact that every time that we receive a new text message, our phone doesn't get heavier, because some of us wouldn't be able to carry our phones by the end of the day. Now, the last sentence says waves always move through something called a medium, and a medium is kind of the material that the wave is moving through. So if you're thinking about like a classic water wave, the material is water. But if we're talking about a sound wave, the material is air. Sound waves vibrate the air as they move through it, and that's what we detect in our ear. Radio waves, like the example that I gave with your cell phone, radio waves move through something called the electromagnetic spectrum. So all of waves have to move through something. Some of those things are physical, some of them are not. So in your notes, I've given a couple of different examples already. Come up with 3 things that move in waves. You can, if you've paid attention to the video so far, I've given you at least 3 different examples. Go ahead and jot that down in your notebook. And so like I said, there are 4 parts of a wave that you should be able to identify given a diagram like the one that I have on top here. So the first thing are the crest and the trough. And the crest and the trough are the top and bottom parts of a wave. So if I kind of circle them on this diagram, the crest is going to be the absolute top of the wave, and the trough is the bottom of the wave. You can think of it kind of like a feeding trough for animals. It has to go down and you put the food inside of it. Or like the crest of a hill. Most of us are familiar with that. So the crest and the trough are the top and the bottom of the wave. And part of the definition is these are the points where the wave is furthest away from its origin. And what that means, what I'm talking about with the origin is kind of a line that if I was to divide a wave perfectly in half, that's the origin. And so at the crest and the trough, that's as far up or as far down as we can possibly get from that kind of that middle line. And the distance from that middle line to the crest or the trough is what we refer to as our amplitude. So the second kind of idea that you should be able to identify is the amplitude. And the amplitude tells me how tall the wave is, or how big the wave is. And so I'm looking at the distance from the origin all the way to either a crest or a trough. That's going to be our amplitude. In some things like sound wave, amplitude tells us about the volume of a wave. And then finally, we've got what's referred to as the wavelength. And the wavelength is literally the length of the wave. You can split it up into two different words. It is the length of a wave, and it's going to be the distance from one crest to the next one, or one trough to the next one. And so that tells us the length of the wave. And that's something that we can measure in typically in centimeters or meters, but it's always measured either crest to crest or trough to trough. Kind of the easiest way to do it. So those are the 4 parts of a wave that you should be able to identify successfully. And so if I was to give you a diagram that looked something like this, you should be able to tell me, okay, well, this right here, that's a crest. And I know that I've got a trough right here. And the amplitude, that's going to be the distance from here to here. And my wavelength goes from one crest to the next, or one trough to the next. And you should be able to identify those things on a diagram. So if you need any help with that, you can refer to the previous diagram, which will kind of identify those stuff for you. Now, once we've got our basic pieces of the wave identified, we can then look at what's called frequency and period of a wave. So you should be able to calculate the frequency and period of a wave. There are some equations here that you will need to know, and so this is where the math kind of kicks in. And so frequency and period. Frequency is the number of waves that go past a point in 1 second, and it's measured in hertz. And so if I have 15 waves that go past a point in 1 second, I would say that the frequency of that is 15 hertz. And so in order to calculate my frequency, I'm going to take the number of waves that I have, and I'm going to divide that by the amount of time that it takes for those waves to go by. And so this, again, if I had 15 waves in 1 second, that would be 15 hertz. And the abbreviation for hertz is Hz. If we want to talk about the period of a wave, the period is the amount of time that it takes for one complete wave to pass. And frequency and period are opposites. And so if I wanted to measure the period of a wave, I would take the time that I have and I would divide that by the number of waves. And this thing is going to be measured in seconds because I'm describing how long it takes for one complete wave to pass the point. And so again, if I was talking about the frequency, if I had 15 waves in 1 second, I'd have 15 hertz. If I was talking about the period, I would have 1 second divided by 15, and I would get a number that's very, very small. So those are the 2 equations that you will need for at least this beginning part, and I'll kind of circle those here so that you can make sure to write those down. And so this one is for frequency, and this one is going to be for the period of the wave. So given an example problem, 15 waves pass a point in 3 seconds. What is the period and frequency of the wave? Well, if I look at my previous example, I know that I'm going to take 15 waves, and I can divide that by 3 seconds. There we go. And so I know I'm going to have a frequency of 5 hertz. And if I wanted to solve for, so that's my frequency. If I wanted to solve for the period of the wave, I would take 3 and divide that by 15, because it's basically the opposite. And if you do 3 divided by 15, you are going to get an answer of 0.2. So this is my period my frequency over here. The period of this would be 0.2 seconds. It takes 0.2 seconds for one wave to pass that point. Now, the third and final thing that I want you guys to get from this set of notes is that there are 2 different types of waves, and we're going to be looking at transverse waves and longitudinal waves. So you should be able to kind of compare and contrast them. And they're very easy to compare and contrast because they're kind of obvious. A transverse wave is a wave similar to what you think of with water waves. If I have my medium, kind of like the water, my transverse waves, they go up and down. So like a sine wave in math, our transverse waves are going to oscillate side to side. That means they move up and down, or side to side repeatedly, or they move up and down repeatedly. But either way, there's this kind of motion that happens. And water waves are a great example of a transverse wave. So most of the waves that you traditionally think about are transverse. Longitudinal waves, on the other hand, longitudinal waves do something kind of weird. They stretch and compress, and there's sections where they are kind of stuck together, where the waves are close together, and then there are sections where they are stretched out. Those compressions, those areas where the things are tight together, those are called compressions. Areas where the wave is stretched out, or where the medium is stretched out by the wave, those are called rarefactions, which is kind of an interesting word. So that's one that I will frequently see students kind of get confused about. So a rarefaction means that our wave is stretched out. Think about it, it's rare to find a wave in a rarefaction. Okay, it's happening less often, if you will. And so longitudinal waves would be like a sound wave. Sound waves are longitudinal. They're made by areas where the air is compressed and areas where the air gets kind of stretched out. And so those are going to be are two different types of waves. So kind of giving you the written version, longitudinal waves, they don't have crests and troughs. They get what are called compressions and rarefactions, like I said before. Compressions are places where the medium is kind of compressed together, no surprise. And a rarefaction is a place where the medium is stretched out, or where there are less waves present in that medium. It's kind of got it stretched out. So if I was to give you an example of something like this, I could identify that I have a compression happening right here. This section, you can see those waves are closer together. And right next to that, I've got a rarefaction right here where things get a little bit more stretched out. And so that would be a good example of a compression and a rarefaction. I'd like you to add 2 examples of a transverse wave and 1 example of a longitudinal wave to your notes. Those will be handy as we kind of go through this unit. And then finally, kind of wrapping things up here, and you can pause the video if you need to do this activity right now. Give me just an easy little compare and contrast. How are transverse waves similar? How are transverse and longitudinal waves different? So they do have some things that they have in common. Yeah, they are both waves. That's an easy answer. But what are some ways that they are different? And hopefully you'll be able to get through that without too many issues, and you'll be ready for our next activity.